Okay, hello everyone. I'm Carlos, and today basically we're gonna have a little demo about the blind bit library. It was previously done using bulletproofs and with the specs a little changed. So now everything has been updated and refactored to basically be used with PLONK, which is the new zero knowledge algorithm that we have been building here in Dusk. So yeah, we can start. Uh, it will basically be about the proof of blind bit, also some related stuff that I think that's interesting for everyone to also know. And yeah, so basically to set a little bit of background here, blind bit is one of the four Genesis contracts that the Dusk network would have. And it's responsible, as its name says, for basically providing all of the logic and the functionalities needed to perform the blind bit protocol over the SVA consensus algorithm. So to summarize a little bit, the proof of blind bit basically what tries to do is to be a proof which lives inside of the blind bit protocol, whose objective is to basically select the new block generator for a round or an epoch or a single block or whatever it is. We need to do it with zero knowledge properties. Here is where PLONK enters into play. Basically, the zero knowledge is needed because we need to prove the ownership of the bit, and we need to prove the correctness of the score that we generated for the bit. So the bit itself is the structure generated to be able to participate in the consensus as a block generator. And it's basically done through a lottery process. So this bit contains a lot of fields, but probably the most important ones, or the ones that I would like to mention, are the eligibility and expiration TS, the prover ID, the score of the bit, and commitments hiding the values or the blinders, which are fields that should be private and only known by the person or the user who is putting that bit into play. So once we have our bit, for this bit we can compute the score, and the score is basically a semi-random function that with the inputs that our bit has, it's able to produce a result which is between a range. And when we analyze all of these results, we can set a logic that says, for example, the biggest one is the one who will be the responsible of being the block generator during the next round or the next epoch. And that's why we call it a lottery, to put it in some way. The correctness of the bit, as well as the knowledge of the inputs and some other stuff, are all of them included in the blind bit proof, which is the main focus of this demo, and we will be showing it later. So in respect of the circuits, and I just seen that I took the photo with my mouse here, but hope it will be fine. Basically, we have one circuit, which is the blind bit one, but we can split it in two parts. The first one will be the score generation circuit, which takes, as you see here, 1088 constraints or gates to be represented in the PLONK constraint system. And inside of the score generation circuit, we basically prove that the score we generated for our bit is correct. So basically that we are not cheating in order to get a privileged score and therefore have more chances to be the person or the user that is elected to be the block generator during the round or the epoch. Basically, apart from proving that some fields required by the computation of the score are on ranges on which they should be to be acceptable, to put it in some way, we also need to prove that the prover identity generated with the fields of the bit, which is the step one, so it's a pre-image check, it's correct. So obviously we cannot cheat because apart from our secret, we also have the hash of the bit sub y structure, which is basically the one that contains all of the information that is relevant for the bit. So therefore, if we change whatever it is from here, we will get a different prover identity than the one we should got. And therefore, we will make all of the proof change. I made some examples to show that, so we will see it later on the demo. Then the overall circuit is the blind bit proof, which contains in the step 9, as is mentioned here, the circuit of the score generation. But apart from that, here we are proving basically, well, a lot of things, but to be precise in some of them, which I think they are really interesting in respect of the development that we have been doing. We see the opening proof, which is basically showing that your bit is placed on the Merkle tree, which contains all of the bits. So basically it's telling everyone that you can trust this bit because this bit has been published on the bit contract and it's stored on the tree there. So I'm not cheating because that bit has already been placed this block or on previous blocks. We also need to make a pre-image check of the bit, which includes the commitments, which includes the encrypted value in Blinder, the public key, the randomness, and a couple more fields. So with this pre-image check, we are basically doing a consistency check, which means that if we cheat here while computing or bit sub y, then the Merkle opening proof will not be the same one or will not be consistent with this step because we need this bit sub y in order to perform the Merkle opening proof correctly. So therefore, there's no way to cheat here. So if you try to cheat on 2, 1 will fail. And if you want to cheat in 1, 2 will be impossible to compute because it's a pre-image check and therefore you have 2 to the power of 256 different possibilities. So even on the whole universe time, you will not be able to check all of them. Then we have some range checks where we are basically checking that our bit is valid during the block height that we are actually in. So it's not more than the expiration date or less than the date when it was published. We then check the commitment, which is basically used to provide that we know some secret fields that we use to generate the bit, which are the value and the blinder. And then we have some extra range checks to basically be sure that the value is not representing some number that we will not want to see here because it could cause problems. So we constrain it to be as maximum to the power of 64. And then we check the prover ID, and also we are checking the hash of the secret. So basically, as the bidder, you need to prove that you are the one that posted the bit. Otherwise, if you are not the one that posted the bit, it's impossible to generate that circuit. You will not be able, never, even if you have like a supercomputer or whatever it is. Once all of these steps are done, we obviously need to check also that the score that we generated for that bit is the correct one. So why we built all of that into a library, we did all of that work in respect of zero knowledge proof and that stuff to provide all of the functionalities needed by the blind bit contract or the bit contract. So basically, this contract is the one who is responsible of managing all of the interactions within the bit contract and the storage of the bits and basically all of the process or all of the things that interact with bidding basically and choosing block generators. And all this contract is able to call these functions or have this logic basically because we have defined all of this logic in the blind bit library. I will elaborate a bit more later about that. As we saw, we have a Merkle opening proof, so an inclusion proof on a Merkle tree. And that's something I would like to highlight. Even I will not like elaborate more on that because probably Chris, who is the author of most of this stuff related to the storage, is the one who will give a demo. But I think that it's important to know that we're not using normal Merkle trees in the sense of the structure is the same, but they are trees that use the Poseidon hashing algorithm to hash towards the root. So why Poseidon? We used Poseidon because it's super cheap or cheaper than SHA or Blake or other hashing families to be used inside of snark circuits. And that was something we were really looking for because it would be like a massive problem if the opening proof takes minutes or even more. So on this way, we guaranteed ourselves that the Merkle opening proofs will be as short as we need it and as performant as we need it. And also we need these Poseidon trees because the data that we need to store inside of them, it's not the bit directly, although we do it because we use the bit as the key, but the value is the encoding of the bit as a BLS 12381 scalar. So basically Poseidon, it's an algorithm that only knows how to hash BLS scalars or scalars of the curve where you define the algorithm, in our case, BLS 12381. So we basically needed a way to translate our bits to single scalars to then be able to perform these Merkle opening proofs. And that took some time to us in order to develop, but now it's actually working, and the results that we are getting are pretty good, I would say. So I'm so happy with that. That also benefits us in the sense of now we have all of the storage in the bit contract directly. And therefore, that means that we don't need to be worried about the synchronization between a node set living on the bit contract and a Poseidon tree living on a Rask server or Dusk process. And I think that this solution about unifying all of the storage with Poseidon trees in the smart contracts is one of the best decisions that we have taken. So yeah, just wanted to basically give a thought on that. So now going for the demo, we are basically going to see benchmarks over the score generation function circuit and the blind bit proof circuit. And apart from seeing the results, which, by the way, I anticipate with the computer that I'm using will not be awesome, we will also check that the consistency of these circuits is the correct one. And therefore, we will try to cheat a little bit and try to get a better score than the one that we should have, or things like this. And we will see that the circuit then causes a failure on the proof verification. And we can go first for the score generation function to see basically how it performs. So here, basically, I am creating a bit, a random bit, and I'm basically proving that the score generated for that bit is the correct one using the gadget that we basically did with Dimitri and Tog, which is quite extensive, as you can see, and contains some range proofs, as you saw on the previous slides. So let's go and run it. It might take a little bit of time, basically, because my machine is running on an i5 and has been on for, I don't know, like a week or two. So it will go pretty slow, but I think that the results will be able to show that we optimize the circuits a lot, and we have like the capability of proving the scores so fast, which I'm really proud of and happy for. It will take some time because we need to compute a dummy trusted setup to basically test everything. So for the rest of things, it will be quite fast. So as we see, we have 1081 constraints for the score generation circuit to prove that it's being computed correctly. And it took 1.2 seconds. So pretty decent, considering that we are basically doing like 5 range constraints within this proof and a couple other extra things. Now what we're going to do is basically try to cheat in another test that I have down here. Okay, so yeah, to show basically what I did here, I created a bit. When I generate the bit with the new function, it basically computes the score and computes the prover ID and computes everything. And then I said, okay, now I'm going to cheat, and I will say that my score is now this, okay? So this is not the score that I should be getting due to the fields that I used here, but I will try to cheat and edit my bit, and therefore I will try to prove its correctness, and we will see what happens. As you see, well, I will remove that, which will be more clear then. I'm trying to check that the verification of the proof is done correctly, but I'm editing the fields, so I'm trying to cheat. So what we want to see here is an assertion failing, saying that, so basically C-Rust telling us, hey, I cannot verify that proof, or that verification was not successfully done. So cargo test, release, and the incorrect score generation proof. So it will take a little bit of time to compute the trusted setup, but I think that it's pretty easy to see what we're trying to do, even if you don't understand Rust. Okay, so as we expected, we got a failure, which basically says assertion failed. And the assertion that failed is basically, I tried to verify my proof, but it is not working. And it's not working because as you see here, we got the score of the bit and other field, which was R1, which is the reminder. And we tried to fake them and set a different value, which was not the one that we should got from the bit that we input. So this is everything from the score generation perspective. Now we're going to check the whole blind bit proof, which also includes that score generation function. And what I want you to see is basically how many constraints every one of the steps is taking. And then we will consider basically if it's worth it or not, or basically how much time everything takes and how fast or not it is and optimized. So I will go to the blind bit proof file. Here I have all of the benchmarking stuff. And we are going to check the correct blind bit proof to see all of the benchmarks. Feel free to check the benchmarks that we obtained for PLONK, which are posted on the repo. And you will basically be able to see that for the amount of constraints that the blind bit proof circuit takes, we should be proving it in somewhere between 4 and 6 seconds or something like this. Okay, so here we have some results, which I will explain now. We see the constraints that the Merkle opening gadget took, which are 29,531 constraints. This is obviously the biggest part of the proof because we have a tree whose height is 17 levels, and we have an arity of 4, which basically means that for every node that we have, it has 4 child nodes, and for every child node, 4 child nodes again. So as you can guess, we have quite a lot of leaves at the bottom of the tree, and therefore we need to perform a lot of hashes. But if we do it with other algorithms such as SHA or Blade2B, this would be like probably millions of constraints instead of 29,000. So that's a really, really, really good result thanks to the Poseidon hashing algorithm. Then we do the pre-image check of the bit to check that basically all of the fields of the bit give us the correct hash. And as we see, we have almost 7,000 constraints. That's also thanks to the Poseidon algorithm, because with SHA and Bellman, that probably would take 24,000 constraints or something like this. So obviously that's a huge decrease, and we are pretty satisfied with the results. We have a ton of range proofs, which are extremely cheap, I would say. And that's something that we worked on with Dimitri in order to improve the range checks to be as cheap as possible, because we need to do a lot of them. So as you see, we have the maximum one takes 516 constraints, but we have some of them that take like 10, which is awesome. Then we have another pre-image check. And finally, we check the prover ID generation. And at the end, and counting obviously the circuit of the score generation, it takes 44,000 constraints. For me, it was 18 seconds to prove that. With the benchmarks that we now have for PLONK, it will be 4 to 6 seconds probably. So much faster. But as I told you, I cannot do anything else with the computer that I have. But yeah, this is basically all of the results, going in deep into every single step for the blind bit proof. And the last thing that I would like to do with you and show you is that if we try to cheat on the blind bit proof, we will also cause the proof to fail. To do that, I will remove that because I want to see the assertion failing. And basically, what I'm trying to do here is generating a bit. And here I'm trying to cheat by changing the score and changing the expiration timestamp, which is now this number, random. Okay. So obviously that should not be possible to do, and therefore we should see the proof failing due to this cheat process that we did. So let's try to run it. Again, it will take a little bit to compute the trusted setup. I'm sorry about that. Okay, and as we were expecting, the assertion failed and we weren't able to verify the proof because basically the proof was not consistent and we tried to cheat. So that was the behavior that we wanted to show and to see. Finally, going back to the presentation again, basically I summarized a little bit all of the things that we want or need to do. And the most important ones for me are the capability of getting a snapshot from the VM to then gain access to the Poseidon trees, which are stored on the bit contract to perform the blind bit proofs without requiring to go through a smart contract call and therefore having a free proof generation, because it doesn't make sense for you if you want to generate a proof for your bit to pay for a transaction in order to do it. And we are pretty excited about that because we want to test a lot of things and we want to benchmark everything. So yeah, more results are going to come soon. Finally, implement everything that is needed to basically allow Rust to be an RPC server which handles the blind bit calls. So that will be it. Thanks everyone for joining. And if you have any questions, feel free to raise them.